Happy snow day again. Here is our lesson for Lagrange error bound, or the remainder estimation theorem. The homework tonight, though, on page 500, 1 through 5 all, and 7 are review, which are good reviews of building some series and manipulating yourselves into some series. Remember to be very careful with manipulation. There's only certain things you can do. You know, you multiplying x times a function, a known function, Maclaurin function, adding, composing. You can't square both sides or cube root both sides or anything like that because of the infinite polynomial on the other side. So be very careful. Remember, the idea with building a Taylor or Maclaurin series, they are polynomial series. So just because you might be able to rewrite yourself into a series, it's not that helpful if it's not a polynomial series. It's polynomials where the math becomes so nice, easy, smooth, differentiable, integrable, the whole 9 yards. So don't get carried away. Once I learned how to do manipulation, I think, oh, I can do anything. I can reciprocate. I can do, and you can, but the goal is to end up taking something that is not a polynomial and turning it into a polynomial. And now today's lesson is, how good is that polynomial when I use it to approximate? So again, first some review with this number 1, the first problem in the warm-up. This is a third-order polynomial. I've used 3 derivatives to generate coefficients here, as well as the function that I don't see evaluated at the center, which is 0, as you can see, 0, 0, 0, and 0. So this one is kind of a cool problem because it says, looking at this expansion, can you give me these derivatives? This is another way to test your knowledge on the formula, on Taylor's formula, without just asking you to write out the formula. So hopefully by now you know that the polynomial and the function f is the same at the center. So when I plug in 0 here, it shouldn't surprise you that you would get a 2. Right? Plugging in zeros for all of these x's are going to make these terms go away. Now, there's 2 different ways to think about getting the derivatives. Right? I mean, I literally can say, well, if this is p, what is p prime? Go over here maybe. What is p prime? And just differentiating term by term. The derivative of 2 is 0. The derivative of negative x over squared is negative 1/2 x, and then 2/5 x, and blah 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 blah. And hopefully you can see that you're going to get x's all the way down here, and again, when you plug in 0 for x, you're only going to be left with negative 1/2. Following the same pattern, well, I can take the second derivative of p. And remember, the derivatives at the center and the function at the center are all exactly the same. So the derivative of negative 1/2 is 0. The derivative of 2/5 x is 2/5. And then remember, the derivative of this would have been 3/8 x squared. So the second derivative would be 6/8 x to the first, and again putting in 0 leaves me with 2/5. And then of course the third derivative would be at 0 would be negative 3/4. Because again, taking the third derivative here would be the derivative 2/5 of 0. This would be negative 6/8 or negative 3/4. And then blah, blah, blah. I would continue, but when I plug in 0, all of those x things would go away and leave me with negative 6/8, which is, of course, negative 3/4. So that's fine, but I could also remember, without taking those derivatives, I could also remember that Taylor's formula tells me that the coefficients of the polynomial, the formula for the coefficients, the constant comes from the function evaluated at the center. But the first coefficient is the first derivative evaluated at the center over 1 factorial. And if I look at what my first coefficient is, it's negative 1/2. So therefore, negative 1/2 has to equal the first derivative at 0 divided by 1 factorial, which of course is 1. So therefore, f prime of 0 is negative 1/2. Further, the second coefficient, if you remember from Taylor's formula, comes from the second derivative evaluated at 0 over 2 factorial. But what is my second derivative? The second, coefficient is 1/5. So the second coefficient is equal to the second derivative evaluated at 0 over 2 factorial, which of course is just 2. Solving that for f prime of 0 gets me 2/5. Similarly, the third coefficient comes from the third derivative evaluated at 0 over 3 factorial. So negative 1/8 is equal to the third derivative at 0 over 6. Of course, solving for the third derivative at 0, multiply both sides by 6, and I get negative 3/4. So either way, this question we have seen come up a couple of times on the AP exam lately. And it's a really cool question. So, here I have a Taylor series J. Find J prime at 0. Well, again, J of 0 is just going to be 3. J prime of 0, remember, is equal to the first coefficient. Right? Look up here. Darn it. Sorry. Since the first coefficient is equal to J prime of 0 over 1 factorial, therefore J prime of 0 is just equal to the first coefficient. So you might say, well, that's 1/4. But you'd be wrong. You know why? Because don't forget, this coefficient goes with x to the first. Where is x to the first? The only reason I don't see x to the first is because its coefficient was what? That's right, 0. So, be careful. The second derivative evaluated at 0 is going to be, remember the second coefficient is the second derivative evaluated at 0 over 2 factorial. Therefore, J double prime at 0 is equal to the second coefficient times 2 factorial, or just 2. That goes with x squared. So therefore, 1/4 times 2, which equals 1/2. going to write that over here. First derivative is 0. Second derivative is a half. Use the above information to determine whether J has a local max, a local min, or neither at the center x equals 0. Hello, first semester, right? The first derivative is 0. Remember what a first derivative at 0 of a function tells you? You have a horizontal tangent. Tells you have a horizontal tangent. You don't know if you have a max or a min, just if you have a horizontal tangent. However, if the second derivative is positive, horizontal tangent here, second derivative is positive, it tells you concave up. So at 0, I have a horizontal tangent and my function is concave up. Therefore, I must have a local minimum. So I show off. Since first derivative is 0 and at the same place and time, second derivative is positive, J has a local min by the second derivative test for extrema. That's a pretty cool problem, right? Here I am in series, and I'm getting a second derivative test. First fundamental theorem type question. That's clever. All right. This question gets back to Algebra 1. If I want a Maclaurin series, which means I'm centered, remember, at 0, I know how to write sine, right? Maclaurin series for sine, that's the odd one. So I start with x to the first minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the 7th over 7 factorial, so on and so on. So I have this. Check. Now I want to subtract x and add x cubed over 3 factorial. Well, just do that, right? So here's p of x, subtract x from this side and subtract x from this side. Guess what you get? A by. Remember, p of x was sine x, so now I have sine x minus x. Check. Check. Now I have x cubed over 3 factorial. So I will add x cubed over 3 factorial. It's freaking out over here, huh? Add x cubed over 3 factorial to this side, and add x cubed over 3 factorial to this side. And remember, when you're adding with polynomials, you're just matching up terms, by. So now I have p of x, which was sine x, remember, minus x, I already took care of that, plus x cubed over 3 factorial, took care of that. Check. So my final answer is the Maclaurin series, I'll call that M for Maclaurin, x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and just give them enough terms to establish a pattern. And you're all good to go. That would probably be a multiple choice question. Pretty cool, right? All right. So for today's lesson, Taylor series are used to estimate the value of functions, at least theoretically. But we have calculators and computers to do this now. An estimate, however, is only useful if we have an idea of how accurate it is. When we use part of a Taylor series to estimate the value of a function, it's the end of the series that we don't use. We call that a remainder. I want you to think about if I have a third order polynomial, which means I've gone out to using the third derivative, right? Then all the rest of the terms, and remember, you're plugging in a number really close to the center, so you end up with, if your center is 0, you're ending up with 0.1 minus 0, 0.1 every time you use one of those polynomial terms. If your center is not 0, if your center is 2, well, you're going to approximate numbers like 2.2. So your distance would be 2.2 minus 2, which is still then, you're just putting teeny numbers in and raising them. So when you think about your polynomials, you've got x to the 7th and x to the 8th and x to the 9th out there at the end or the tail of the series. So you're adding all these teeny tiny numbers and collecting them all into one term, and we're going to call that term the remainder. Well, what we want to try to do is find out what is the size of that remainder. So if I start with e to the negative 2x, and I'm centering at 0, so remember that's where I'm going to radiate out from when I go to the right or left. And I'm going to use the polynomial to approximate e to the negative 2 times 0.2 of negative 2x when x is 0.2. So I built this from e to the x, right? You know that hopefully e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and I'm just doing a composition where in place of x I'm just putting negative 2x. There's negative 2x, negative 2x, negative 2x, negative 2x, and they asked me to do a fourth order. Well, I used my calculator and I plugged 0.2 in for x, and I got this. How good is this approximation? Again, with a calculator, I can tell. I can actually ask the calculator, what is e to the negative 2 times 0.2? Or negative 2x when I put 0.2 in for x. And I get that second number, and of course I can figure out what is my error. Okay? I use absolute value because I only care about the magnitude of the error. And that's pretty freaking small, right? So using this fourth degree polynomial to approximate this got me darn freaking close. It would be nice to know if I want to use this polynomial to approximate e to the negative 2x, I want to know what is the maximum. What's my worst case scenario that because I truncated, I cut off the infinite series that e to the negative 2x is exactly equal to. I cut it off after x to the 4th, or using the fourth order. How all those other terms that are over here, the x to the 5th, the x to the 6th, the x to the 7th, blah, blah, blah. Collect all of those terms together, add them up, and that's the error, right? Right? That's what I didn't include. So what is the total that this error could be? Well, Taylor has a theorem, and it looks like that. Notice that, as impressive as this might be to pull out at parties, this is just your polynomial out to the nth order. And then this is everybody else. All the other terms just collected into one package. So truncating, cutting off your infinite polynomial here and using it to approximate f of x here means that this is your error, right? That's how far off you could be because you didn't use these terms. What is this maximum? There it is. Lagrange came up with this form of the remainder theorem. So all the other terms, my error is this. Now notice, this looks hopefully somewhat familiar. This number c is what I'm plugging in, and this number is somewhere between the center and the x value that I'm approximating. That's Lagrange. He at least is not wearing a wig, but he's still, I don't understand why these guys were, well, I don't want to be too judgy, but don't seem too attractive to me. Anyhow, there is an easier remainder theorem besides Lagrange, as much as Lagrange looks all fancy in his formula. There is an easier remainder theorem that I will teach you, but not yet. The reason I want to teach you the harder one first, plus the easier one only works if your series alternates, right? If my signs go plus minus of my series. Lagrange will work all the time. So we better practice using the nastier one first. Then, if you have an alternating series, I'll give you an easier version. Now, sometimes AP will call this, and they'll say, what is the Lagrange error bound? And that means use this formula. But they don't always call it Lagrange. Sometimes they call it the Taylor remainder, or the remainder of order m, or the n, or the error term. And it does just look like how you create the next term in any polynomial series, right? This over here, this is your derivative of n plus 1, so the next derivative, the next factorial, and the next power. Again, A is your center, x is the number you're trying to approximate. This is the nebulous thing, some c. This should remind you of the mean value theorem. This c is guaranteed by the theorem to be between the center and the x value that you're approximating. So the problem is that c value, unlike in the mean value theorem, is challenging to find. But remember, when I'm just talking about error, I really just want to know, what's my maximum error? What's the worst case scenario? So I'm going to call m the maximum value of the next derivative. If that is so, and again, all I care about is the magnitude, then the magnitude of my remainder theorem will always be less than or equal to this number m, which remember replaces this up here. If I could find this exact value, that'd be swell, but I normally can't. I most often can just find a maximum value of this. And I'm just calling that m here. And I'm using absolute value bars here because I don't care if I go to the right or the left or the center. But my maximum error will be guaranteed to be less than or equal to this value if I can find, the maximum value of the next derivative that I would use after truncating. Next derivative after truncating your series. The remainder estimation theorem gets us close to the actual, or puts a bound, a maximum bound on the actual Lagrange error. Oops, sorry, this is important. The book, I think, uses, I'd have to look at the new book, but certainly in our older book, the formula that they gave, oh no, yeah, it's the same here. On page 498 in our book, it gives us the remainder estimation theorem, and it uses m. But m, it has this r to the n plus 1, so this is a little bit simpler version. AP does not care what you use. So back to our example here, where we built e to the negative 2x and cut it off. Remember, this is an infinite series, and we cut it off here. Okay, it's not the infinite polynomial. I'm going to use the remainder estimation theorem and say, what is the maximum error? Now, we were actually able to compute the real error. We'll talk about that when I'm done with this example. But let's pretend we couldn't. Let's just say, here is, using e to the negative 2x, its polynomial expansion, cut off after the fourth derivative. What's the worst error involved in using 0.6704 in place of e to the negative 2, where 0.2 is used for x? So this n goes with this 4. When did you truncate? So the remainder truncating after the fourth derivative will be less than or equal to this m, which we have to find. So this n is 4, this n is 4, this is the x that I'm plugging in, so that's 0.2. This is my center. And these, again, are all my 4s. 4, 4, and 4. So I just have to find this freaking m. To find m, I have to find the next derivative. So I'm after the fifth derivative.
Finally, someone!
Remember, the 0.2 came from here. What x am I using to approximate? And 0 is my center. So, the maximum of the fifth derivative between 0 and the x I'm trying to approximate is at 0, where m is equal to 32. How the heck did I come up with that? Well, I had to, of course, this is why you do derivatives first, I of course had to say, well, what is f prime of x? F prime of x is e to the negative 2x, spit out the negative 2. What is the second derivative? E to the 2 times e to the negative 2x, spit out the negative 2 and get 4. And the third derivative. And the fourth derivative. And finally, the fifth derivative. So I'm going to look at the absolute value of this function on the interval So up here I have the absolute value of negative 32 e to the negative 2x. The window I looked at was between negative 0.5 and 0.5 because again I'm just going from 0 to 0.2. And if I graph that, and I didn't really know, I took algebra 2, so I don't know, can you see that? Right, so I do know what exponential functions look like. Right, that's what I put in. And if I hit trace, at 0, I'm at 32, but at 0.2, I'm lower. Therefore, what is the maximum of the absolute value of the fifth derivative, which was the next one after truncating, was at the left end point 0. I guess I could have dragged that over here, huh? Silly. Anyway, seen it better, huh? Anyway, that's how I got this 32. And I'm going to put that 32 here. And I'm going to say 32 divided by 5 factorial times 0.2 to the fifth gave me this value. Right? This is the maximum error. And remember, if we go all the way back, that's right? 1, 2, that's 0.0008. What was our error all the way back here? I can't do this too fast or it freaks out. Okay. That's the error that I got. This error is less than 0.0008. Close, but less than. So let's try this again. And this time we're going to use this example. Find the maximum error when x minus x squared over 2 is used to approximate ln 1 plus x. And the x's that I'm going to put in and use this polynomial expansion are between negative 0.1 and 0.1. So this, remember, was generated. This is a manipulation of one of the formulas in your textbook on 491, which was ln of 1 minus x, I think, right? No, it's ln of 1 plus x, it's right there. And this is after 2 terms, where one term where I'm taking derivatives. Since I have x squared, I know this is, right, since I have x squared up here, right, I've used the second derivative. So I go about finding the first derivative and the second derivative, and then I'm going to stop at the third derivative. Do you know why? So, remember, any polynomial expansion, Taylor's expansion, Maclaurin, however you want to say it, f of 0 plus the first derivative of 0 times x to the first, second derivative at 0 times x to the second, and then this is the rest. R for remainder or R for the rest. This is everybody else collected into one term. So that's how I know, because I saw x squared, the rest is after I use the second derivative. So I know the n for me in my theorem is 2. That's how I knew to go from, to start with f, take the first derivative, the second derivative, and then this is the derivative, bing, 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 that I'm going to be trying to find m. So, I can write the exact infinite series then as 0 plus x to the first minus x squared over 2 plus the rest. Notice I don't have an approximation, I have equals to. So my remainder estimation theorem, or my Lagrange bound, says that this term, which is my error, will always be less than or equal to, use your 2's, right? I have, since this is a 2, the next factorial will be 3 factorial, the next power would be 3. This x is going to be between negative 0.1 and 0.1. This is my center. And now I just have to find m. Since I don't care whether I go right or left, I just put 0.1 in here, because it doesn't matter if you put negative 0.1 or 0.1. I'm going the furthest away from the center that I'm saying that I'm going to go. Any x between negative 0.1 and 0.1, go the furthest I can. So again, my worst case. And then I either use my calculator or just my knowledge of rational functions. You know what a constant over x cubed looks like. Shift it a little bit because you have an x plus 1 here. You know what that function looks like. So on the interval negative 0.1 to 0.1, this function decreases. Therefore, its maximum value must be at the left endpoint. Right? What is the left endpoint of my interval? Below left. There's my left end. So, take the derivative, evaluate it at the left endpoint where you're going to find the maximum value of this function on negative 0.1 to 0.1. I stored that in alpha A. No, I didn't. I stored it in alpha M. And I took that value and I divided it by 3 factorial, and then I multiplied it by 0.1 to the third. Negative 0.1, 0.1 matters not, right? Because you're taking the absolute value of this distance over here. Right here. And there's my error. My error bound, my maximum error. Here's me just showing the calculations. Now I wrote it down as a rounded value, but when I had my calculator, so I stored it, again, in alpha M, so I can maintain all of those decimal places. And there's my Lagrange error bound. I made a little chart to compare, because again, we have our calculator, so I can actually find my exact error, but showing that what the Lagrange error bound does work, if I use the right endpoint of point 1, so the furthest away I was going to go from the center, and I plug point 1 into the original function, right? This is f of x, and this is the polynomial, oops, sorry, 2 after this, of x. Using x minus x, right? This is a parabola, right? Negative 1/2 x squared plus x, right? This is just a parabola. Using this parabola to approximate the natural log function, how bad can I be? Well, there's the exact value of ln 1 plus x. And there's the exact value of x minus x squared over 2. What's my error? How about if I go to the left end? Because I don't necessarily am balanced, you know, on the right and left of the center, as to if you have the exact same error on the left as you have the right. So that's what I get using when I plug negative 0.1 into the natural log function. Here's what I get plugging negative 0.1 into that parabola. Pretty freaking close.
Those shorts are going to fit under your...
They do.
And again, this number, 0.00004,
Okay, gloves and hat, let's do that.
was the worst my error can be, and as you can see at my left endpoints, I'm actually less, right? But remember, the Lagrange error bound just, it overcompensates, right? It's going to give you the maximum error. Oh, rats. We've been doing so good, and now my my computer decided to spaz. So excuse me for a second. Go to the bathroom, go get a drink.
We need to get a picture of this dough when we come back in. Okay? Your pants are down in the basement, so are your boots. Let's go down there and get those. You got your feet away.
There we go. Only had one slide left to go anyway. So as I kind of hinted to at the beginning, or towards the beginning, you don't want to do Lagrange. You don't want to do all that. I have to take derivatives. I have to evaluate, usually graphically, what the derivative looks like so I can find its maximum value on the interval. So I would like to avoid him if I can. Not today, but there are ways to avoid him. Most notably, recognizing your series. If this series that you've written falls into, did it come from a geometric series or is it alternating? There's some ways to get you around Lagrange, but we're not going to do those today. But what I am going to do today is a couple of your homework problems with you. So as I said, numbers, the very beginning of your homework is kind of a review. So let me just get out my copies of the homework and the book. There we go. Number 1, you should recognize from the lesson. Number 1 asks you to build a series for e to the negative 2x. And then number 2 and 3 ask you to manipulate from cosine and manipulate from sine. Number 4 is ln of 1 plus x squared. So again, from your page 491, you can look at ln 1 plus x and compose x squared into that. Number 5, I want to remind you, number 5 looks like this. It says it gives you see how it presents. Oh yeah, so number 5 looks like this. 1 minus x to the negative 2. And it asks you for the 4th order Taylor polynomial. So I could build this, or I could recognize that if I integrate, so if f of x is 1 minus x to the negative 2, if I integrate both sides, then I get the antiderivative of f of x is equal to, right, the derivative of the inside here is just negative 1, so I just have to have a negative on the outside, and I'll get, and I'll power this up. So add 1 and I get negative 1 and divide by negative 1. So I just get 1 minus x to the negative 1. But of course that's 1 over 1 minus x. Which is, of course, is my geoseries, where a is 1 and r is x. So building my geoseries, so if doing a 4th order, so instead of building this, I can just say, by finding derivatives and using Taylor, I can use my geoseries formula where I have a times r to the 0 plus a times r to the 1st plus a times r to the 2nd. Remember, there's no factorial in geoseries, right? That's just in Taylor. But of course, this is equal to the antiderivative of f of x. But I'm trying to get f of x, right? So the antiderivative of this polynomial is equal to the antiderivative of f of x. I didn't want the antiderivative of f of x, though. I wanted f of x. So guess what I can do? Take the derivative, right? If I take the derivative of this side and the derivative of this side, the derivative of an antiderivative just gives me the polynomial that will be equal to f of x, and differentiating a sum is the sum of the separate derivatives. So what's the derivative of a constant? 0. Whoops. And then I think it said it wants you to use this to approximate the function at point 2.
What?
I keep putting on my boots before my snow pants.
Oh, I'll come out with you guys in a little bit. I have a couple problems to finish, then I'll come out.
I'll just try to do
So I just plug 2 into here, point 2 into here,
I keep putting my boots on.
which will be and I'll get a number which will approximately be the original function, oops, at point 2. Yay. Number 7 was a cool problem. Oh, no, not number 7, number 11.
Yes.
Number 11 asks you to do a graphical analysis. So it uses ln of 1 plus x again. And it wants you to look at the graph of the polynomial expansion.
Look at that.
Did you get it over? Hey, Dad? Can you, head out and start shoveling
And
the
it
driveway?
says
We're gonna do
if you stay between negative 0.5 and 5, when will this polynomial after the... Which order? Where do I cut this off?
Then you do a little shoveling too, go through the garage and open the garage door.
Where to cut off the polynomial?
Yeah. Oh, good. There we go. That's
So that, your error, and remember your error would be your ln minus the polynomial,
doesn't bother me.
right? And just again, take the absolute value. So that the error is smaller than 0.001. So check this out.
No.
Let me see. Ah, very nice. I like that.
Okay. Okay.
So check this out.
How's it feel? Let's get the boot on. Booty on.
I went to my window and I made my x min negative 0.5 and 0.5. I went to my y min and put 0.002 in there.
Good?
And then in y equals,
You put that on and I'll get your gloves.
I graphed ln of 1 plus x, my original, and I graphed through the third order. Right, I graphed through the third order here. So here's my polynomial, x to the first minus x squared over 2 plus x cubed over 3. And in y4, I graphed the freaking error. Right? Then, check this out.
I didn't find it. I was agreeing with Mom. Because I understand Z.
In y5, I'm graphing the constant function 0.001. Wow. Now, let's look at, first, there's the original. Here's the polynomial. A cubic function that is going to behave just like this natural log function on this interval. Let's see how close they are. Oh, rats, you know what I should have done.
What happened on there?
Mine.
Like this? Okay. I think those are the ones you put in.
Turn this off. Turn this on. Fix my window. See if I can see more of it.
You like the Titans?
So you see the bubble there?
You like the Titans? Watch the Titans.
Right? As long as I stay in that interval,
Alright, I'll be out in a minute.
even make it bigger. There's ln of 1 plus x, and here's the cubic. Look how closely the cubic function models it from negative 0.5 to 0.5. Right? Now, at the center, of course, they're equal. And then towards the left and right ends here, you're going to get worse and worse. So, I'm going to turn off the original. I'm going to turn off the polynomial. And I'm going to turn on the graph of the error and the error bound that I want. And I've only gone out to the third order. This is my error. These are my error values. And that's the error bound. Notice that from here, my error values are below 0.001. But as soon as I go out all the way to negative 0.5 and to 0.5, I have error values that are above 0.1. So what happens when I start to add some more terms? Minus x to the fourth divided by 4 and plus x to the fifth divided by 5. Now I gotta go turn this off. Graph. Oh, but look. So can you tell? Can you tell that when the 0.001 line draws, do you see that I'm getting there, right? I have more values to the right and left of the center where the error stays below my bound. So let me try a couple more. And the question is just asking, how many terms does it take? So I just keep adding. X to the sixth divided by 6. And instead of graphing that, I'll just tell you that wasn't enough. But when I did x to the 7th divided by 7, rats. Supposed to be minus x to the 6th. And plus x to the 7th. Look at that. Takes a while. And notice again that we're not perfectly balanced around the center. Error values are not balanced. As a matter of fact, had you seen, I believe that if I had only shown you the graph with the x to the 6th term, I think the right side was below the arrow bound, but the left side was not. It was not till I got to the 7th, x to the 7th over 7, where both sides, to the right and the left, were under the arrow bound. So I like this problem because it is kind of a visual of what's going on when you're finding an arrow bound. So I found this bound, and it took me 7 terms to go out. And some of your homework problems are going to algebraically ask you to solve for that. So, number 19, I think, is another one I was going to do with you, because there's a cutesy little trick they use here too. Number 19 talks about sine x and using a cubic. Right, that's x to the 3rd over 3 factorial, which is just a cubic function with a leading coefficient that is negative, -1/6, x cubed plus x. Using that cubic to approximate sine x. And the question says, for approximately what values of x? So it's asking you for the interval, what x's around the center, can I use x minus x cubed over 6 instead of sine x, and I won't have any error greater than 5 times 10 to the -4th, and give reasons for your answer. So, since this is sine, and I know sine alternates with all the even powers dropping out, what if I say that I'm going to add 0x to the 4th over 4 factorial, and I'm going to call this, if sine x is f of x, I'm going to call this my polynomial of order 4. Since it has a 0 coefficient, aren't the values that I get out of this the same that I get out of x minus x cubed over 6? And therefore, I can say, when I'm using my Lagrange remainder theorem, I can go to the next derivative, right? So I can just make it a little more restrictive. So I'm going to use Lagrange and say that r sub 4, right, and if you just thought of, you might have thought of just using r sub 3 because the last power that you saw was a 3, but since adding this term